if you don't put your visage here in front of the camera, your face won't be recorded, but your voice will be recorded. Okay, so last time we left off with this problem, and I don't want to spend the whole, if we can't find a solution within, or if we can't at least find an approach to how we can solve it in the next, let's say, half hour or so, then I say we move on. But let's just try and restate the problem. So we have this NPQ and there's the NF, which is a number of factors of P. So there's a few functions, and there's this random function which is defined like this, which we programmed here. And I don't know, maybe you can read through, Andre, maybe you can read through this and start asking questions. Maybe that's a better approach.
Yeah, the problem itself is difficult already.
Yeah, I have to remember myself too.
Yeah, I forgot to.
Okay, so we have this NPQ. I think this is correct, right? This is this function. It iterates through the random, or it generates this random sequence. And this is defined as the sum of these elements of the sequence. So here you see that it's summing up the elements of the random numbers. And then the trick here was we want for this we want the factorial.
Oh yeah, and there was you can take the mod during the summing already.
Right. So, but this is an optimization, right? This is the idea here. Is, if you notice, you're always multiplying with quite large numbers, and this mod is basically an optimization to make sure it stays in the long, as a long, because you'll notice that the next sequence, the next element of Tn is always mod P. Oh no, this is the mod P here.
Yeah, so
we do a mod somewhere else here. This is the optimization I was thinking about.
oh.
This is actually part of the random number sequence.
Yeah.
Right?
Yeah. Yeah, I think we were doing mod in the rest, but we removed it.
Right, we removed it. I will note that we do have this result. We were able to reproduce this, I believe. We were given that 3 to 10,000 mod 3 to the 20 is this. 310,000. Well, okay, I think I have to go through the thing, sorry. No, sorry, I have to execute the code again because the notebook was closed in between, and therefore the code is no longer loaded. Okay, so this, and did I not? It has to be defined. Why is it not defined? Pardon me.
Maybe the import, Python import is not executed?
It should be.
What name was not defined?
N.
Name N?
Oh, the plugin of importing the Cython
And if
module
you-
is not.
I understand. No, this is CDEF.
Yeah.
This is only you can only reference it from within
yeah.
here. Okay, fair enough.
So NF. Okay.
So NF works though, probably. Yes. Okay. Yes, and we get out this number, which looks remarkably similar to this one. Hopefully.
Oh, yeah. And then you get the other one. NF. You already did the 61.
Yeah.
Well, no. This.
We run into optimization issue. Oh.
No. This is not the. This is 10 to the 4. The problem says 10 to the 7 and 61 to 10.
And 10 to the 4th works?
10 to the 4 apparently works. That's, I don't know if it's particularly fast, okay?
10,000 what?
Yeah, so I doubt this will finish.
Fine.
Well, maybe it'll finish, but we have a way to go up until 10 to the 7.
We can do some optimizations.
Yeah, that's the thing. Okay, so we are convinced, I suppose, that this stuff works. Ah, never trust the
There
keyboard.
was a delete cell.
Yeah, I wanted this.
Command DD.
Okay. Yeah. I'm not sure what this 9 is. It's print. Okay, this is the print.
That's the time it was.
Maybe. Let's see. So the thing was, I think we came to the conclusion last time that there's nothing we can do about, I mean, we have to calculate n, and I don't think we can get away from, I think this is going to be part of the code.
Yeah.
I think that was our conclusion.
No.
No?
There was something that I realized last time. There was the number of factors. They will never. You can get the number of factors. You can just count that for or not.
Maybe. You say, so remember it's the number of factors.
NF is the number of factors.
NF, yes, the number of
in
factors
fact.
P.
And
Right.
fac is the factorial. So
Correct.
you don't need to calculate the whole factorial.
Yes.
Correct.
You can just take the number of factors p for each term in the multiplication.
You mean the multiplication, by the multiplication you mean the factorial that produces the
Yeah.
factorial. So this is,
Can we
And actually, the number of factors p is actually only so in that whole factorial, if p is a prime, was p a prime? Yeah.
yeah. 61.
You can skip in the factorial all numbers that are not multiples of p,
Sure.
because you only need the number of factors p.
You mean we don't need to calculate n, but not sure if it's the bottleneck here. If we can.
Oh, I think it is. Oh, I think it will be if Q gets larger. Or it will be one bottleneck. There are two, probably.
But the n fac is the factorial of n p.
Can we did we time n just n?
No, we didn't.
Okay.
No, but did
This one got finished, apparently.
Mm-hmm.
I don't know. Well,
no, but there was something with what is the loop actually?
what is the loop? This one? Or which one?
Yeah.
So this is trying to find the number of factors p.
No. Oh yeah. You already have the NF then.
Mm-hmm.
Yes, but it's
That is-
slow.
No,
as-
you have the n. Is the n slow or is taking the NF slow?
I think both are slow. Notice I have a print statement here,
Here it is.
And we haven't reached it yet.
Is n divided by p?
Yes.
You only need to take the numbers, of course, that are already a whole multiple of p. This was straightforward. Oh, you have n base p, that is it. N base p is the print that you have.
No, this is this doesn't do anything.
No, it is just print the n base
Right.
p.
Yes, this is, and we're not. It hasn't printed yet, so it hasn't gotten past this call yet.
So it did not get to nf.
No.
N itself.
Yes.
And n itself, you also only need to calculate.
Well, if we go 10 times more, I mean, this is calculating already for a minute. This is not, I mean, this is not 21 seconds or whatever the claim is that we can do.
I hope that is possible to skip every 61.
Should we start?
That you only need to do n in range 0 to q plus 1, that you can skip every 61st.
And skip every 61st.
Is there a...
No, because we have to get the factorial, right? I mean, this is an optimization in that we don't actually calculate the factorial.
Yeah, that's very
but
good optimization.
Yes.
And the whole n, do you need to calculate that?
Maybe no, I don't know. I think n is a big int. Yeah. So this is a huge number. So sure, if we can avoid calculating the whole huge number, then sure. But I'm not sure we can.
You mean like we go for all the factors we replaced by a loop and we calculate it inside, so...
Well, this res is plus tn times pn. And what was pn?
Make that...
pn to the power of p. Or at least...
Pn starts at 1. This is p to the power of n.
Mm-hmm.
Right, exactly, because we don't actually perform the power each time. All we do is multiply it by p once through every loop.
Yeah. Multiply by p every loop.
So like we make that loop inside the...
So you count the numbers of multiples of p. That is the end of the number of factors.
But it's added on, it's not, right, it's the sum, this is the sum, it's summing over these multiples and then taking the factorial of that. So I'm not sure what the relation is, maybe it's there, but I'm not sure what the relation would be.
And if you keep the...
You can just get like only one p in fact. Because every term in the sum is multiplied by p, you can only get out 1p from the sum.
There is some mod situation that you take a prime, power, something, mod, another number, and those are prime relative to each other.
Coprime? Is that the word?
Yeah, I don't know. And then you can swap them, or what was it?
Coprime.
The same way as RSA produces its result.
Okay.
That is that you have.
Should we Google coprime or something like that?
Yeah, and then mod. Coprime mod model, yeah.
co-priming. GCD is 1. I think that's what does mean co-prime.
See, no, that's not it. That is, we may divide by b when working modulo a.
The greatest common factor is 1. The co-prime integers. Can you go just a little bit down? Maybe search for GCD.
Here's GCD. That's they make the thing you want to
Yeah,
search
that
for
is-
as an
that is-
image.
That is
Okay.
co-prime, yeah. That was, but now the results of that is that
The number of integers co-prime to a positive integer n between is given by torsion function.
yeah.
I
that
remember
is-
something about the torsion.
Wait, the number of integers co-prime.
Yeah, but it's
But-
not about co-prime. It is about
Is it
that
not?
rule that you get out when taking mod of one and mod of another. That you can.
Well, let me just understand what co-prime means again.
Where was that formula with mods?
Yeah.
You just had something with a mod formula. Properties, yeah, there. That I think that bottom, that a consequence of the third point.
I don't see it.
It's like 4 and 9 should be co-prime if I understood it correctly, or? Like for
Yes,
example,
yeah.
like the-
Right, yes. For, yeah. Only one is.
Only one is the common difference.
Yeah.
I
But
think
is that
it-
not applicable to this?
I think it's about 61 and that prime number that is taken modulo in the random function.
But for prime number is everyone is co-primed.
Of course. So it is surely co-primed with the 505.5. And the
Yeah,
Q is
yeah,
10,
of course,
and-
yeah.
but Q is 10 to the 7th. Is there a reason that we cannot skip? Somewhere you have Q n in range 0 to Q plus 1, but I think n can skip every 61st. Every 61.
Okay.
I suspect
Well,
that you in that way can divide out that 10 to the 7th.
do I have to, like a barbarian, click on something? Okay. If this is true, what you say, then I should be able to.
To do the end with the step function.
Right. So you want to skip every how many?
61.
Or in this case, third.
Oh yeah, P. So it is P.
Sounds abenteuerlich.
No,
No.
something else. What went wrong?
Didn't provide argument in or
No, you did it right. That was what I meant, but it is not giving the right answer.
Yeah.
Is it something then? Is there big ints involved in that?
Yes, res is a big int.
Yeah, that is always a very slow function.
Yeah.
And is there a way to keep res already in the?
What about keeping the TN in a thing? In a list?
Oh, of course. If you do the res,
We do. If
You-
we do the sum of that list, we will have the rest, but we keep them. In
The rest.
Non-summed, not summed.
Mhm.
the res is a sum.
Yeah.
Yeah.
But the sum of the modulos is also the modulo of the sum is also the sum of the modulos.
The modulo of the sum is the sum of the modulos? What?
Yes.
But not the other way around.
Okay, but what is this with the list? I mean, I can convert this to a list, sure. Let's do this. I'm not sure what we're going to achieve by this, but we can do it. And then I could, just for correctness sake, I will just do this. Just to verify.
Oh, yeah. Was it right already?
I don't think it's finished.
Such a list is also very long.
Yeah. Okay.
Can we loop through that list and we don't do while n? We do the same in range.
But you don't have a print at the. You do the n is n.
Yeah.
Can you print something there already?
Where? Here?
Yeah, yeah, just that n base p is alright. Those two lines. It's already indicating how many digits that the number is long.
Ah, yeah. Okay. I guess we don't care about the n then. Sorry. Compile.
That was quick. And right.
Yeah.
I think instead of doing while n and compute the sum of res, we go over every element of the list and do the same thing for all elements.
We do the same thing for all elements.
Like the n receive n divided by p. Just replace the while n superior to p by for n in and
so you want to, let's see. And you want to see
n receive n div p and is it the same? And rest.
Well, I'm replacing this, so I guess n part. And you want to do this? But
yeah,
I'm not sure what you're going for.
it will be something like sum.
I'm not sure why this would work.
Res. Now you have res as a list.
Yes.
And then that's also the result. Now n is delivering a result, a list as result.
Yes.
And then for n part and n part, yeah.
Maybe we do while n is more than p. But it's like small chunks. Instead of having the big sum of factorial, we have it in like small chunks of the whole factorial.
But this is sum. Why would this result in what we are looking for? We're looking for the things that the number of times p is a factor of n, which is itself a sum and not a product. I mean, if it were a product, of course, yes, then if p is a factor in the part, then it would also be a factor in the factorial, or in the whole thing, but we're doing sum, so it's not.
Yeah, but the sum, but every number in the sum is 61 times as big. Because it's p to the power of p.
Oh. Every number.
Every tn is 61 times as big because it's multiplied by p. So if you take only the last one, you already are say within 1/61st of the total. The sum of powers. That's a simple formula. That's something like do Google sum of powers. I think it is. Yeah, there is yeah.
Just like I know NP complete, there is no K.
Yeah.
Format is there is no K superior to 2. You can found that.
No, I mean this full hours. Here, this one expresses 1 plus 2. If you use that.
That's the description.
Yeah, that one.
Right, but that's just
but
an
what
expression.
what
does
is
this
the-
tell us?
Yeah, and
See, that is the polynomial. That is normal. For p is odd.
Ooh.
It is n over n plus 1. That's the normal one. That's
yeah, it's only for odd stuff.
But we have odd stuff. P is 61 or 3 in our case.
that database of big numbers, that OEIS.
Yep.
Yeah. 537. Oh, that formula is even more difficult.
Conditionalized.
More generally, and what is the B? The Bernoulli number, yeah, of course. Oh, shit.
But
I'm not
okay,
sure
so this
how
isn't a
can-
general thing. This is just
No, that's only for the power of 1, and then the power of
Okay.
2 and the 3, and Bernoulli is delivering the higher powers.
Okay.
Oh, there is a specific case for if the power is pair is odd, and if the power is even. Yeah.
Yeah,
it
the
goes
power is
up.
odd, so it falls off. That what I read that too. There was something.
What?
Yeah, the power is odd. We
If
have
the
the
power
61.
is odd, or if the power is even. There is different formula, but I don't know how.
For an odd power greater than 1, the sum is a polynomial in n having factors n square and n plus 1 square. Can you go even more up? There was something that there. The polynomials are divisible by a square because the Bernoulli number is 0 for j is odd. Show that first formula. Oh, that is the sum for an odd power is given by. Yeah, that is not making it easier, I think.
What is C1?
And the C's are
Constants.
I don't see what the C's are.
I think we went too far.
yeah, this is too far. Now there must be a simplification. There must be something.
Proof with complex number. C. Riemann.
Yeah, of course, it is the Riemann zeta. That is also true. But
Of course, everything is related to each other.
no, but all all summations of powers are all in that Riemann zeta. That's it. That is.
Okay.
So we are solving the millennium problem.
Okay. Is it fair to say we don't have an approach here?
Yeah, but we have we're summing another higher power of p each time for all n's,
Yeah.
and then taking the number of p's in the factorial of that total.
Can we do a while inside that loop? The same.
Yeah.
No, no, where we just for testing. Yes.
Yeah, but
And
you
we
don't
do
get it
while
out.
n is bigger than p, just to the same. That one, just we put it inside. Yeah. No, we keep the loop, but inside the loop we do the while. Yeah. And rest will.
This is supposed to do something? Okay. Res starts at 0, I guess.
Yeah.
Yeah, sure.
No.
Nothing to comment.
Wait, it gave a number.
No. It's unbound local.
It is unbound.
I think max res. No, res. Res is 0. And what is n? What is n? N is nothing. Yeah, at recht.
Oh,
What does n start as?
oh,
And receive n part maybe before the while.
Okay, but why don't I just then take the last element in n parts? Why would I go through everything if I'm just going to start over it?
you have enough at the last part. Because you're doing plus with a number that is more than, that's around 61 times smaller. So there is not much to be found there anymore. There's at least no extra factor 61 anymore in. In the end, here you're finding the number of factors the number of factors
Yes.
p in this huge number.
Yes.
Well, no, in the part.
Yeah, now in the part, but in the end here you were finding it in the total huge number.
Yes.
You were finding the number of factors p.
Yes.
But the previous one is around 61 times smaller. Not really, because Tn might vary a lot. But at least this is a mod in which 61 fits max 3, 4, 5, 6, 7, 8 times. So you actually need only to add up the last 8.
I have to, so I can cut off this list, is what you're saying,
You
to the
only
last
need
8?
the last approximately 8 or 9. Because the rest is all too small to deliver in the addition more factors of 61.
Would it be the other way around? Because this is, we're talking about the lower digits, aren't we?
Yeah, but the Tn is always smaller than 61.
Yeah.
That means that you only need exactly the last one.
I only need exactly the last one. Okay.
And the
let's-
rest of the sum of the previous one
Will never add up to another factor 61 anymore.
Why?
Because it's more than because it's around 61 times smaller. So there will not be another factor 61 anymore in this number.
So if just the previous mode is given you the rest of 1, but
Was this your class? This was
yes, this one was mine. Yeah. I put it for you, but
oh,
you.
no.
We can maybe use this one.
Yeah. You have the last number is a really big one. The last number is this one. The previous one is the last one. You have an addition of a really long list of huge numbers. Every time it's a factor 61 in the power, and the factor t that is smaller than 61.
I don't see it.
You go to the original formula. Tn is a number mod p.
Correct.
Tn is thus smaller than 61.
Correct. Yeah. Yeah.
And you do a sum of 0 to q
Yeah.
over a number smaller than 61 times a power of 61.
Well.
So the last power of 61 is surely say every next number in the sum is at least 61 times bigger. Oh no, Tn can be in the previous one, can of course be
Pn. Okay, so it's p to the n times bigger. It's p times bigger.
yeah. It's p times bigger.
I mean, Tn may be smaller, right? Because it's mod p, may be smaller than it previously was.
Yeah. So Tn for the previous factor. But at least the next one, even if Tn is 0, Tn cannot be 0 because it's the p and the 505 are not prime relative. Are prime relative. So even if the last Tn is 1, even then the last number is 61 times bigger than the previous one. It's not 61 times because the previous one can be, of course, 60 times 61. The previous one can have Tn is 60. But the next one has at least 1 times 61 more.
I don't know. Maybe it helps if I try and actually show the thing.
Can you go through them without doing append? Just let them calculate or. Oh, append the list, and now I'm just type the print the last 2 of the list or so. Yeah.
And
last
0?
one is-
What? 0? 0? What?
Last one is 0.
That is strange.
Last one is 0.
Oh, sorry.
Few of them are 0.
Because they are multiple of 61.
No, it's now about the 10,000 and the 3 is P. The P
3.
is 3.
There is big.
Maybe Tn is 0?
There is big probability to be multiple of 3.
So Tn is 0. And if T, yeah. It always does mod mod P, which is 3.
Yeah.
So yeah, and this is just doing mod this, which can be yes.
And they are not relative to prime.
Can be
3
0
with,
mod
3 with 505.
Yeah.
5, 15, 16, 25, 28. It's not divisible by 3.
Huh?
The 50515 number is not divisible.
Prime. But we have 0 mod, that number is would be 0. 0 mod any number would be 0. Or not?
Yeah, how can it be 0?
Because Tn
If Tn.
Tn is 3, so Sn. And Sn is a number that is where is Sn starting?
Sn starts at this. This is part of the.
Oh yeah, that was a stupid number. Yeah, that is divisible by 3.
no,
Not?
no. The sum is not divisible.
This. No, those. I don't know.
Can we take the first elements?
Yeah, no, it's not divisible by 3. There is
What do you want without F?
The first 3 elements, the last one.
it stays 1. Oh, and then it switches. So it's not delivering zeros.
Well, this is you can, maybe this is interesting, I don't know.
Yeah, then it is showing zeros.
I wasn't sure if it made a difference.
So there are lots of zeros.
Yeah.
But there's a random, it seems.
I just say that this is a random function.
Yeah, so it could very well be. But you see, the result is always, it's 0 or it is more than 3 times bigger. No, that's also not true.
But the result, this is not the result, right? This is the partial, this is added together, all of these.
Is that already added or not yet?
This is not yet. I don't know.
So you have Tn and Sn and Tn times.
Or by P, I guess. I'm not sure.
Yeah. Try.
Oh, too large for float.
Ah, it is a big int,
Correct.
and then you're dividing. Yeah, that could help.
I'm not sure what I'm trying to do here.
No, because then it was every time the previous number, the previous TN.
I don't know.
Yeah, because you did times Pn div P, and Pn is the next time just exactly P times this big. So.
I mean, it's just I didn't have any concrete idea about this.
I guess that this one is exactly 3 times as big as that one. And this one also exactly 3 times as big, and then this one is probably exactly 9 times as big, or so, because there's 2, or is it 6 times as big? 7, 6, and this is 4. This is 6 times as big. Huh? On a 2 it gets 6 times, yeah. No, on a 2 it's also 3 times here in the beginning. See? Times 3, times 6, again times 3, and that's, oh, that's not times 3, that's only times 1.5.
Huh? How about
back to 1, it goes times 1.5.
so this is the sum. Oh god. So the empty list, so I guess I have to tell him to do it with 0. Res. Oh right, it doesn't work with this.
Can you do mod res, 3?
Wait a minute.
Res, P. Oh, like that, yeah. Oh, you removed it.
I guess we can do this here.
Yeah, that's what it is. And can you do the mod too?
What?
The mod P. Just to see if there is something.
Res sum mod P.
Yeah. If there is something special happening. Oh. Is the mod always 1?
P is 3. So the sum mod apparently.
Can you do these first 34 for the so the mod P, yeah, it doesn't help.
Okay, but does this help in any way? What is this? Oh, it's 0, 0, 0, okay. I don't know, we can put this on the back burner. I don't know. I don't have the feeling that we're going to do it today.
That res sum mod. And that was always 1.
Correct.
How is that possible?
So Pn is a power of 3. So we're always doing P
Oh yeah, of course.
n.
Yeah, so the mod stays the original one that it started with.
Yeah. Well, I'm not sure.
Yeah, this one is divisible by 3 already because it's 3 times 6. Ah, no.
But Sn goes into this too. So Sn goes into the Tn, and the Tn is taken times the Pn. So this also has to be... no, I guess not, maybe not.
Right, it will be always the first mod. Because every time you are adding to the sum a multiplier of p, so it will be always.
Yeah, but if you go over 10,000, your result will get over that 50 million number, and then you'll get a mod 2.
Do you think if I go far enough, then it will...
If you say number 60.
We can look at the last ones.
Yeah.
1, 1, 1.
It stays 1.
1, 3, 2.
Yeah, of course, because the number is not getting big enough. You see, it was only 80 million.
It's still 1.
No, the addition is only 80.
Oh, sorry.
The addition numbers. Here. Here somewhere. The number that is the number that's added is still less than the 50 million. So you won't get over that, and only after that you'll get something extra from that mod, maybe.
But this is Sn. It always stays below.
Yeah, here for the 3, because the 3 is not 3 times over 10,000 is not going to that.
You're saying this is... Are you sure? Okay.
No, it's of course never going to open because it is already more than 50 million.
Yeah.
No, it's too difficult. I'm curious about the solution. About the solution of other people.
Yeah, well, tough.
Type problem 83.
You can do that in the privacy of your own. Let's just give up.
What was the number of this problem?
288. Let's try and get at least something. This is the only problem with the lowest difficulty that we have. So let's try this one. It's 85.
Yeah, this might be better because I was stepping into the middle of it, you know, it was.
Yeah.
You were already.
Well, and it was a quite difficult one.
Yeah.
So this is the next one. It's probably.
Thanks.
Well, I will just start by generating by generating grids and counting the rectangles, maybe.
No, it's not counting. It is. You have
Okay, yeah. What is the relationship between these?
you have two dimensions,
There's probably symmetry. Yes. Okay. Also.
and in each dimension you have a number of
Yeah.
1 by 1, 1 by 2, 1 by 3
Yes.
times the rows, and then you have the same thing but one less
Yeah.
in 2 times as big. So actually this is
So it's asking how many.
yeah. So this is
So we only need to count
X.
the cases where the
no,
top,
R,
where the rectangle touches the top left corner,
this is Rn.
and then
This is-
divide that by. So divide width and length. How
R
often does it go
times-
width-wise? How often does it go height-wise?
And
Yeah.
minus
Multiply.
1, and this is R times
Can be solved in
3, 2.
2 for loops and just go.
Well, it has to be binary search probably.
It's even simpler. This is total. This is Rn faculty, and in the
What is R?
rows, 2 rows.
You don't know rows.
Yeah, now it is 2 rows.
Okay.
But this one of 1 row high has n faculty. Wrong. It's not faculty. It's n plus n minus 1. It's a sum of 1 to n. Of course, there's one big one. There's 2 ones of one smaller, 3
Yeah.
of another one smaller, until n ones of.
But you can
And-
move it like this way. So it's
Yeah,
counting.
This is one smaller. So this one is only 1.
Mhm.
Then there is 2 of one shorter. There is 3 of another one shorter, and there is n of into total n.
Yeah. Right. You can like move it by one
So
side.
that's n. That's n. That's 1 to n.
Mm-hmm.
So this is our sum 1 to n. How do you do that? 1 to n of n. X. And you have to multiply that by all these can exist in
Multiplied by
all
2,
heights.
by 3, by 4.
they all can exist in all heights.
Mm-hmm.
So this can, so it is actually sum of y is 1 to r times sum is, I think is 1 to n.
We are okay.
Guessing or true?
Okay, first of all, there are rows times columns number of shapes, and these are then we have to count them, I guess.
One plus 2 is 3, and 1 plus 2 plus 3 is 6. 3 times 6, that's 18. So that 18. So it's 3.
About is like this sum 1 to n.
Yeah.
Then you go 2 times the sum, 3 times the sum, and then you go like this.
So that is in total times 1 to number of rows.
And you have to sum it up for sure all together, and then you
Yeah,
are there.
but every height of rectangle has the same horizontal possibilities. So that is again.
It depends on if it's even or odd.
See? It's a rectangular grid. So if you have of height 1, you have one of 1 wide, 2 wide, 3 wide, 4 wide, 5 wide.
Oh, yeah.
You have the sum of 1 to n.
Okay, but if the rectangle is 3 high,
then you have for each of those horizontal various widths, you have again the ones of 1 high, 2 high, 3 high, etc. So you have 3, if it is 3 high, you have 3 of 1 high, you have only 2 of 2 high, you have only 1 of 3 high. So it is again total times the sum. So you have these two. That is, what is it? R times R minus 1 over 2, was it that? And n minus 1 over 2. And find the number, find an R and n where the total is the closest to 2 million.
Well, that's just binary search. If we have the formula, that should be this lit list of the problems. You're saying you have the formula?
Yeah. Oh, yeah. Just the 1 to R is R times R minus 1 or R plus 1.
And
Better than this.
is this supposed to be n? Okay, this is n. Okay. N is okay. N is okay. I can't differentiate your R and your N from each other.
Oh, yeah. This one is only R's and this one is only N's.
Okay.
What is it? No, N plus 1, wasn't it? Say 5. And 1, 2, 3, 4, 5. 15. So it's 5 times 6 over 2 should be. So this is plus. This formula is wrong remembered. This is the formula. If you have 4, you do 4 times 3 over 2. 1 plus 2 plus 3 plus 4. No, 4 times 5 over 2.
At least it produces the right number for this case. Okay. Let's try some things. So def num rects. I will call it rows and columns, if you don't mind.
Oh, you can do div 2 if it's quicker.
Div 2?
Yeah, you can do div 2 if it's quicker.
It doesn't matter. I don't know, just for sanity.
You can better make that. You can better anyway do div 2, then you have integer calculations instead of floats. But each time div 2 is of course in the end div 4.
No.
So you need to find 2 numbers that are div 4, the closest to 8 million. Or actually, no, not.
So for 2 million rectangles. So this result has to be 2 million. And we have to know the grid. Okay, but this is, we can vary the width and height. So this is not just binary search.
No, just let R count from 1 to million and C for until 2.
Well, we can make it as wide as we want, and then we can shorten it until we get to a point where it crosses over, and then we have our point.
You
right?
can, of course,
Because it's symmetrical.
Yeah, we can like take them big and we have the like maximum, or as soon as we are getting close to the 2 million we stop. Not sure.
take C as the one that delivers 1.9 million, and then step up until you pass it 2 million. Take some 5 more.
But it can be like for less C and more R, we can find the 2 million, something closer to 2 million. You know?
So actually, for each R under oh wait, million and million, and there is R times R, so it is 8 million in total. That is only going to in numbers until 8 million, root of 8 million, 3,000 or so.
Does it right? No.
So you can calculate them all.
Sure. Yeah. Okay. Then I guess for rows in range, I don't know. Do we even need to go that far? 500 maybe?
No, I think you need to. Of course. Because.
Yeah, maybe smallest is like big number. Then we do. The,
you only need to go to.
We do our numRects minus the smallest.
You only need to go to the root of 3,000. That's less. That's only some 30 or so. What is the root of 3,000? 40? 50? You only need to go to 50. 54. Okay.
Why 50?
Because C will be the bigger one in that case until you go to the million. Now,
okay, this has to be okay.
55 to the power of 2 is more than 1 million.
No, this won't matter for the result. So if okay, let's see. N is no.
I would start C at 55. Oh no.
I think both are like we can change C or R. We are looking for the
closest one, yeah.
For the no matter of which one.
And print.
We can print it, sure.
Of course, you don't need smallest. You need closest to 2 million.
Yeah. So delta.
Yeah. You can take the smallest number more bigger.
So this would be. Right,
Plus
leave it at
affinity.
this. Yeah, just everything is okay.
Can you type plus infinity? Isn't that max int?
There is nothing in Python with.
I think so.
Maybe some libraries there.
Yeah, of course. Started. 2 million, of course.
Max size.
Yeah. And you cannot change. Oh, S equal 60. I guess 63 minus 1.
Wasn't it? Oh yeah.
Yeah.
Ah yeah. Okay.
This max size is not max int or something.
I think in Python 2 it's max int. Okay.
I think with the smallest delta we should take it bigger in initialization.
Oh, sorry.
No, it's already alright. It's finding
It's pretty close.
36, 77. Okay.
What is they looking for? Find the area. So they're looking for
R multiplied by C.
Okay, fair enough.
Okay.
Can we look to some
There's some
NLP solution?
some nice solution that someone invented. 10 minutes, yeah, of course.
This is C.
Yeah. it's
Yeah,
also,
they never-
straightforward. It's extremely straightforward, this one. See, he just
He's counting the number of he's actually going through the whole thing as well. Yeah.
rectangles. Rectangles yx is, and the rectangles is that formula that we did with the n times.
Yeah.
Wait, there is an analytical way. There was a.
The thing is,
Can you do that?
the interesting thing about this one is, I think so the problem is released at some point, right?
Yeah. And then
Probably
10
at
minutes
midnight. And 10 minutes later, he has a solution.
But can you do the text of there is an analytical way to solve this one? If you imagine 8 plus 1 vertical lines. Yeah, that's the same thing. That's there's so many ways of picking 2 vertical lines. B plus 1 over 2, yeah. Yeah, that was our formula, but then that was all.
Maybe by hand. He did that by hand.
Huh?
He did that by hand. He found the formula then by hand.
Yeah. That's A plus 1 and B.
What is the value of A and B in our case?
Now we had the R and the C. R times R plus 1 over 2
What
times
was
C times.
It was 36 and 77.
Yeah, and what was. But that's not really an analytical way to solve the problem. That is an analytical way to calculate the number of rectangles.
But this is analytical, I think.
Oh, he was going over all. Once your width is over 1 million.
Yeah, that's the biggest thing that could possibly satisfy. And then you go downwards.
Yeah, but once your width is over 1 million, there is no variation in the height anymore. So you only have that width number of possibilities. And it's anyway too big. 3000. Once your width is over 3000, you're already over the 8 million. Yeah, there, the formula, and then the previous one. That was the one that did the formula.
What?
I think
There was
in the bottom.
one further down, I think, was it?
One further down.
Yeah, there was someone who said,
okay.
I used the following formula.
which is over 5 for our formula, is doing it by 0.5, which is
there's no way to. I thought someone found a way to determine analytically the number closest to 2 million. Next one.
Yeah.
Last one. Then, oh.
Unless you want to keep it.
Keep it.
You can keep it.
Sorry, I didn't know why.
That's okay. I think I have to start printing new ones. Well, no, not yet. So, pick one, please.
yeah.
82. You can open.
What was the previous thing that you had in the screen?
Where? Pardon me.
Minimal part sum.
Okay. The minimal path.
By 80 matrix. Of course, you don't go left. It's not allowing going left.
Right, yes, you can go right, down, up. Should we start from reverse, from the back?
It doesn't matter.
Doesn't matter.
From two ways, it does not even matter. You have to test all parts. And as soon as you're bigger than the previous one.
Well, no. You start. We have to at most test 80 paths. We have to at most have 80 paths simultaneously. Right? So we start on each of the things, and we step further along the path, along one of the paths.
I think 80 to 80 is not that big complexity. We can brute force it.
Okay.
It's more than 80 because
we can compute all the paths and
but on every step to the right, then you can choose how many times you go up or down.
3.
Well, you can go up as many as you want.
As many as you want, up or down, and then
Right.
again a step to the right, and then again as many times.
But every time you step, the path gets the sum gets longer. larger.
Yeah, but it might be useful to go 10 steps down and then take that path, because there are a lot of smaller numbers.
The point you're making is that the complexity is not so small as 80 by 80 might suggest.
I guess more.
But maybe if you go like so much down, so you add them more. So probably the better way would be go as much as possible horizontal.
I was already imagining that this one would be a better path.
Maybe.
So going left, even.
Yeah, but you can't.
But because numbers are all, I don't know how big the numbers are, but
like I think the probabilities are that the more horizontal is the better. Than to go vertical, because there you add more and more.
No, I think there might be some tricky.
Maybe there is like here in this line less, so you should go like.
Yeah, that's the numbers are very unequal.
The largest numbers looks like it was 10,000 or something.
Yeah, it was all max 4 digits.
I need to remember which way. Okay. But
Yeah, it's not like 80 by 80.
It's more, I think, huh?
On every step you have multiple. You have 80 options, so you have 80,
Yes.
80 times 80.
Yeah, 80 times 80 times.
No, that's all. Every step to the right, you have. So each of these 80 steps, you have to choose on which point you will go the next step. So it's 80 times 80. There's not many.
No, it's like for this one, you have all this. For this one, all of this. It's not only 80.
I think more, because if you have 80 times 80 matrix, then just from the first column you have 80 options, and every of those 80 options has another 80 and another, and next one has again, and they can also go up and down. So I think it's much more.
No, so it's 80 times 80. Every column has 80 ways to go to the next.
Yeah, but from every column you have, in the one column you have first column you have 80 options where to start.
Yeah, but that's only starting. But in the second column, you arrive, and then you have to choose on which of these numbers you go the next step to the right. So that's 80 possibilities. And then on that next column, you again have 80 possibilities to choose where you do the next step to the right.
It's 80 to the power of 3.
No, 80,
No.
80 times 80 is simply
3.
No. You
80 times 80.
not. I mean no. But if you pick out one cell, then you can go up, down, or right. Right. You can't go.
Yeah, but you have 80 columns to work through.
Yes.
You cannot go left.
Correct.
First column you have 80 possibilities.
Correct.
Second column you have, again, wherever you arrive, you can choose on which of these
No, and
80 numbers you do the step to the right.
No, you do all the other parts. And you compute them.
You can go also up from that one, and then
You can
then
go
right, and then
20 up.
Yeah, exactly. So
And then-
so
So the second column
it's more
also
than
has
80.
No, the second column has 80 options too, where you do the last step. It's actually 79.
Yes. So for this one, like for just reading this and this, it's 80 times 80. Like you go by column and by rows.
Yeah.
But if you like select this one, it's let's say like we are going this way. Selecting this one, and then we have these possibilities. This way is like our first look. This is our first n, first 80, and we have 80 possibility. But for this cell, we are also computing the path of the all other cells, so it's another 80. That's, you know.
Yeah, but not true.
Like this would have to.
You have 80 columns,
Yes.
and in each column you have 80 possibilities.
Yes.
So that's 80 times 80.
It would mean like that this one would be only 5 by 5 would be 25 possibilities.
No,
then, right?
it's even more, even less, because the last one you don't choose anymore. You stop it. So it's actually 20 only.
But I think you can find just from that one you can find.
Try.
Okay, first, second, third, fourth, fifth, and I'm starting only from one, right?
Yeah, 5 for the first,
and
oh wait, you don't go. No wait, this was already starting at the second one. You don't do this.
Yeah.
From each number, you only have 4 possibilities to get to the right side.
Well, how come I can go up, I can go down, I can go right, and I can select whichever way I want, huh?
Up, down, left.
Yes.
Up, down, and right.
So I can go also like this, if it's the shortest.
Oh yeah,
way.
yeah, but
Yeah.
for the first time, you for the first, of course, you only go to the right. For the first row, you don't.
No, probably I
go,
don't see why. Why would you?
because you then have a number too many in the sum. You need the smallest sum.
Yes, but
You could just as well start in another row.
Yeah, okay, that's true. But from the second column, it's already like it can go like this, it can go like this, it can go like anyway, basically. So it's much more than I think 25. I believe.
Yeah, true.
If we like our first and
It depends on the numbers which are in.
Oh,
yeah, if our first n is like going by
it's
columns,
80, faculty 80. Or
Yeah,
80,
it's something
high
like this.
80.
Yeah,
Whoa.
exactly.
But I think I have an idea how.
It is fairly a lot. So you have to stop at least at the moment you come at the last sum you found.
Faculty 8 is definitely closer, I think.
Oh shit, this is a lot.
No, but I think we have.
Each you have 80
factor.
Yeah, you have 80 choices where you can do 80.
Yeah, this is what I wanted to say.
80 points where you can have, no, it's 79 points, because once you're on the last one you don't choose anymore. 79 points where you can choose 80 positions. So it's actually 79 times high 80. Yeah, that's fairly a lot. But on most of them you can stop as soon as you get.
I think it is better to go from the target, because what I think you can do is you can propagate the shortest path backward.
It doesn't matter. It's
It does.
as if you turn the matrix around and start at the other side.
Okay, fair enough.
It's the same.
I mean, this is, I don't know, maybe it's just easier to think of this. So if you want to say, assume that 18 is the one that is the shortest path, you look at the choices you have and you add 18 onto that. So you add 18 onto here, you add 18 onto here. And then you propagate this forward. So you add 121 onto here and onto here, and so forth. And you propagate, and eventually you find that, and you always only propagate whatever is the lowest path that you currently have available to you.
Should we? I think also if we do this, we should also propagate to the 111. But this is really,
Yes.
Yeah.
Yes, because okay, let's just assume if we propagate to left, at some point this will be larger, and then we will see, okay, 168. Okay, this is the shortest path we know about.
Yeah.
And then we propagate onto here, and then we see maybe we're bigger than the other one that we currently had as the smallest possible.
I think the problem we can't compare paths until we reach the end, because it may, like, at some point it seems to be larger, but if we continue with that it will be less than if we continue with the smaller one.
No, but it's clear. If you start at one horizontal, you have the sum.
Yes.
Then you start with the next one, that is go That is why how you did it. One step down and see if that number first step down is already bigger than that one at the right. You can already quit. Then you take one further step down.
But if we, what if like the next one, if we select that one, it will be much less. Just I mean, for example, we choose this one and not going down, but this number just next to it is much lesser than if the all other possibilities of the selected path.
Yes, I think it could happen. I think also that.
But I think there is a trick in the matrix.
I think you can just stop only when you reach the total sum. You can go one way, and then you have one sum, and once you go another way and you reach it, then you can give it up already. So you don't need to calculate all of it, but you don't know it until you reach the lowest. Basically, you can then replace it and go again way and search like this the shortest, but other you still have to go all the path. I think.
I think we should like continue.
Is there a need to determine short paths? Say to determine groups of numbers under 1,000, or numbers to avoid, say whole rows of numbers over 5,000.
What?
No, thanks.
I'm not sure what you mean. We have to have the minimum path.
Here it is clear that this path is less than 1,000.
Right.
So as soon as you hit the 965 and you already had the 342, you can quit. So these two can never be be used. This one can never be useful because it's next to this one, and next this one is these two are already more than the paths you already had.
I think
so you can have a lot of stops because sums.
That's what I'm saying. What I tried to illustrate earlier. You try to find all possible minimal paths, right? So you propagate the smallest thing here. We start here because it's the smallest number. Then you propagate whatever the path that leads to that is. And in this case, actually, I think it's only to the left because 18 is smaller than 150.
The right column you don't go vertical anymore.
Right, but pardon me. Let me just. So at some point you get to this to the top three. So you get to here, and this is something like 350 something, and you see, okay, 350 something. This is larger than something that might lead to here, right? 111 is smaller than our number going to here, so maybe everything else to the left of this is 1, and therefore we continue here because this is the smallest path that we know of. So we continue there until we see that whatever way we go from here, it's larger than this, and then we continue on with the smallest one from here, and we just go between whatever the shortest paths are that we know about, and eventually we'll get to the left side.
And left or right starting is no matter. You just have to work from left to right, and say you start here. You have this row.
Yeah.
This is 800, 1,100 or so.
Yeah.
And then you start with go here down, and you see, oh, this is more than 800 more. Okay, stop. This one down. Oh, this is already also more than that. So you don't go down here. You go down here, and you go to the right, and then you see, oh, we're already more than.
Go up.
You might go further down, but then you see 746. Okay, give it up. Then you go.
I would say we always have candidate
here one
paths.
further down, and you see 800. Okay, stop, because this one is bigger and that one is bigger, so it has no use. So from this one, you already have only next to this one. You only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 options to test. And then you're sure over the other ones are surely not. So in a matrix of 5, you only have on this one only 11 options to test, whereas it was actually 4 to the power of 5. You would have, for the first one, you would have still 4 to the power of 4 things to test, so that was for 1600, so it would be 265 to test, but on the way you already find that lots are not useful, so from the 265 you only have to test some 10, so you're actually reducing a lot.
Yeah.
Sometimes we can like go further because it may reduce our threshold.
Yeah.
If we feel it's like, for example, our initialization would be something random, like from left to right. But then, and we are building our shortest path based on that. If we find something is longer, so we don't take all the other possibilities. But
I think we have to go through, I mean, we have to be sure that it's the smallest path.
Yeah.
So we have to...
Yeah, the first like threshold would be, we want to make... If it's like too random, so maybe we end up treating more
I don't know.
cases as it should.
Maybe what about if every cell would have one threshold, like build it, you know, like that you go one path to another, and every cell will keep the lowest sum, which you basically, if I have, for example, this 342, like the second row, third column. So I will this will remember the lowest number how to get there basically, and wherever another pass will come there, it will quit automatically.
Is there a way to start in the middle? You mean?
I was meaning that every cell would keep from the second row, let's say, will keep one value, like a dictionary or whichever to define, and whenever you reach this with the higher sum, then it stops basically.
But it can be part of another shortest path. Or can
I don't think, because the way out of the cell it's already doesn't
because
matter.
you already executed all the paths, and it seems like they lead to longer paths.
You already executed the shorter path to that cell. So basically, if you go through another path to that same cell, then the sum will be anyway higher already.
Yeah.
Does anybody have a recursive formula in their head?
No. No, just do 4.
I forgot, I missed the 18. Okay. Okay, and now I guess
Sure.
too bad.
This is nice. I'm enjoying this.
missed it. Comma. So now I have it. Okay.
And is it really the same one?
Wanna bet?
Yeah.
Yeah. €5.
No.
So
But I still
131.18. But you have the thing on here on the paper, right? 131.18. 331 down the bottom left.
Correct.
It's correct. I think it's correct.
There's a 7 and a 9. What? You swapped the 7 and a 9.
Where? Bullshit. Okay. So the recursive solution. So we wanted to have some kind of find path, whatever grid.
Oh, yeah, of course.
And what do we
Dijkstra.
From a position. Find path from a position.
Does Dijkstra would solve this, wouldn't it?
Can you do
It's the edges graph, yeah.
find path grid from a position in that grid?
Starting from a position, right? And
then in the end, of course, you start find path from 1.1 or 0.0.
Well, but we have to
have
find
it
multiple.
recursive. Yeah, but once you are on, say, on 422,
Yeah.
you have to.
Also make the decision.
You only have one path from that position. But if you start here, you have.
No, that's not true.
You can have still up and down.
Yeah.
But the first column that only goes to the right. So the position that you start here is always going first one to the right and then up 1 or 2 or 3 or 4 up and then of course from that position again get the path.
So I think
And the position is
so I think what we will do is for I guess for row in grid I guess just row index in range len grid, and then our position is starting, and I guess grid is row column, so
isn't grid
row index and 0,
isn't grid a
or we
global
can just
variable?
do
Or is it
row
automatically?
index call index. Grid is passed as an
Put the
argument.
column first. Don't care.
So no, you think this is
Why 0?
because this is 0.
Oh.
So we go through all of these, starting from each of these positions. And in here, I think we just say, okay, we go one time down,
and
we
you
go
have the
up.
threshold, and you have the threshold to count.
Well, I think we will manipulate the grid probably, won't we?
You
Or
mean
maybe
the
the-
initial short path, initial one, like random.
Ooh, manipulate the grid.
Well, maybe not this grid, maybe something else.
So you can.
We need to keep, I mean, we need to track the weight of the total weight of the path that we've traced behind us.
The sum, cumulative sum.
Yes. And
Yeah, that's anyway.
okay.
So you have.
Yeah, let's do that. Maybe it's just a parameter.
the sum
path
until now,
sum.
and the max where you can quit.
And the path sum here is very simply, I guess, maybe we just start with 0 and
Yeah,
we
okay.
always by convention, we as first thing
Yeah, but you
add
have to,
on wherever we are. So now the path sum is like this.
No, you start with going.
Let's
No.
forget about
No.
this index
No.
bullshit. Sorry. There's no need for it. And this is
But no, you already have the path sum in. Say you are here, this position.
yes.
You already have this 699 in the path sum.
No, I would say
Because
I mean,
you're
this
now
is
going to the right, and you start on
I mean, this is
this column,
the
and you
convention.
can
You
go
can
up
do
or
it
down.
first, or you can do it when you're there.
Okay. Yeah.
And I'm just going to do it when I'm here, because this way I can just start at 0 and I don't have to pluck out from the grid at this point. How much?
Path sum plus is grid row call. Yeah, and you can go up and you can go down.
I would define one more like such a I with the minimums, basically with the minimum sum, and always
Yeah,
stop there.
and stop where it is. But
So
that is
it will make it shorter.
you have to go up from that point until, and from up you have to check again the path.
Yes, yes.
And then and 1, 2 up you check the path.
We have to go each way.
3 up you have to check the path. And if you're so many up that already in the going up, you cross the end, the highest until now. You start going down also until.
Well, the thing about this solution is that we have to. There's no way we can stop going down. We would go through. We would be tracking through all solutions at the moment, right?
Yeah, no. The moment that you in your sum path sum plus is.
You have something that is superior than.
There has to be some global thing that is shared between them.
Yeah, the max where you quit. Of course, you have on each find path from position, you have your sum is your position, and then you call the find path from position in the same row directly to the right, and you try the one with column in the same column, 1 up, and the one with in the same column, 1 down. Those 3 you have to test from this point off.
Yeah.
That's all. And then you have your recursive thing.
But yeah, but that would be going through everything.
No, of course you have to quit as soon as you're over the max until now. And the max until now you get that out of the first straight one. That is of course your first option in only column increasing and not row up or down.
Until now is the keyword, I think.
Yeah. Now you do path sum. If path sum is bigger than until now, then return. Otherwise, you can.
But I have to resume this maybe later. This.
No, yeah, but give a next line. Path sum, and then if the path sum is bigger than or path until now, that is the global variable then, or the max path. You have to, of course, you have to, as if you are getting with this cell over the max path until now, you have to stop. If you're not,
Mean path.
no, the longest that you have found and the shortest that you have found until now.
Mm-hmm.
Current shortest, yeah, that is. Yeah, and if not, you have to try 3 options. Find.
At most, we might be at the top or bottom, maybe just 2, or we might be completely.
You
on
first
top.
try the one. Of course, row is row plus 1. Column is only plus 1. So now you have to do 3 recursive find path from position grid row column plus 1.
This cannot work. This cannot possibly work.
Why?
Because there's no way to resume this.
Why not resume?
If I'm just returning here.
Yeah,
but it may turn out that row column at some point the cur shortest becomes longer than the path sum that this position is at. So we would have to resume here.
Why? What resume?
Wait, say your let's see. Say you're going along here. You end up here. Then you haven't tried this path, for example. You haven't gone along here. So you've gone here and here, right?
What?
This is the path that you're currently tracking. You're tracking, okay, let's put it differently. You're tracking here and you go to the right. So that here you see you're something like 800, right? The current path is 800 path sum. You know that there are other paths that are smaller than 800, possibly, right?
No,
so
you cannot do that. No, you cannot, because there might be if here is more. You have to do it the other way around. If this path sum current shortest, you have to start that at. Where is current shortest? You have to initialize that somewhere.
Here.
Initialize it somewhere. Yeah. That should be very big, of course. That's 80 times 10,000. Because that is the max, of course.
Why?
80. The numbers were all smaller than 10,000.
Oh.
So the total length is less than 80 times 10,000. Of course. And now, if the path sum is bigger than the current shortest, then you return. If the column is column 80 or 79, what is it? 0 to 79. If the column is 79, then you have 1. Then you say the current shortest is your path sum, and we have a new current shortest. And otherwise, you have to go first try 1 to the right, same, find path from position, otherwise go 1 up first, otherwise go 1 down first. Get the idea?
This cannot work.
I think we cannot like...
From every position, you have a position here.
It cannot work because
here you are.
You have to have a global state for the grid. There's no that you cannot, and this is nowhere. This is not modeled here anywhere. You
are here. You get to this cell with a value of path sum until now is say 500, and you get to this one. You say, okay, we are now on 922, and now we'll call with 922. We start testing this cell, and then this cell, and then this cell. On this cell, you arrive at 9. You start with 922. You get 111, so you're on 33.
Yeah.
You did not have anything smaller than 1033. You say, okay, 1033. Your previous one was 1050. You say, okay, this is my answer. Until now, we are now in column 79. So quit. So the new shortest path is 1033. Now it returns.
Backtracking, okay.
No, not backtracking. It is a recursive principle. You come back out of your function and you do 1 up, and this one finds, okay, we are on 922 plus 965. We are bigger than 1010. So this one returns immediately. This one, 121, says, oh yeah, it's also 10 more. So it also returns immediately. And after that, you return to this one, and you try, instead of the 422, you go to the 342, and try from there, first the right one, then the up, then the back. Oh, back is not possible. Ooh, there's something. Of course, our back is not. Back is.
You mean like because you can select this one, not.
Yeah, if you did go one up, you should not test the cell down anymore.
Mm-hmm.
Yeah, this makes no sense. You add only additional.
Yeah, and it takes longer until you reach the over the
This
maximum.
you
No,
can-
it makes sense because you can like test from this bottom and then all those.
No, but you start here, of course.
If you
Can
start
you-
at column 80 by 80, so it's okay to you are testing all the vertical stuff. If the cursor
If you
is
just
correct.
if you just put now something like next to that return thing, you put the line if you're in column, if column is 79, then we have reached a new current shortest. So current shortest equals path sum and return. And current shortest, oh wait, and current shortest should be a global variable. It's not current shortest should be an overall variable. You cannot adapt that in the call.
Oh, what about this that you will build actually another such an array that instead of current shortest one number, basically you will have every cell will have basically each current shortest so far.
Yes.
Huh?
I think.
Yeah, you can.
I think of this as like a
that makes
wave
sense.
that's propagating through the grid,
Yeah, exactly.
and all you need to do is keep track of the front of the wave.
Yeah, but now you're keeping track of the start of the wave. That's the same. Which if you start on this side and you keep track of what's here, the shortest path, is the same as if you start at this side and you keep.
Yeah,
track of what's here,
I'm
the
not. Yeah,
shortest
it doesn't matter from which side you start. Yes, I know. But I think this is like, yeah. Let's just call this the wave. I don't know. And we just initialize it with, I guess, the initial row
path. Oh, there is still a trick in
or the
it.
initial column. Row 0 for row in grid. So this is the wave of
Yeah, but
maybe not.
I would say just make it recursive. Just say if you're at the end, you can modify your current shortest. That should be a global variable. Just do it. You don't trust it, but why? Where is it? You don't trust it.
Because I don't. I think you have to know about the other paths, and I can't.
Which path?
Well, there are various options that you can go through, right? You can start at any point here, and therefore, when you're looking at one single path and you're looking here, you cannot, with just the local information that you have for this path, may be sure that it's the shortest, because it could be that any one of the other paths
True.
has
So you
a
have to go
shorter way.
totally through.
You have to only do all of them basically like this. But
Yeah.
it's fine if you do all of them and you take just the minimum.
Yeah, but there
one.
will be later on some optimization. Of course, there will be points where you actually can register current shortest from here, maybe.
Yeah.
That should be an optimization, but start with just going through, and you'll anyway won't do more than 80 sums in general for each point, because more than 80 you'll get over the. So actually the order is 79 high 80, but on each of the starting points of the 80 starting points, you won't do more than 80 paths, because on average, or not more than 160 paths or so, until you get over your current smallest.
Yeah, it depends how many paths you do. I think it depends how lucky you are with this. If you start from the, if you are.
Yeah, but all paths, you have to follow all paths, but each path can stop, of course, at the moment that you get over your limit.
Yeah.
Okay, what do you think of this? So I have here the path sums, which is basically the grid with all zeros, right? 0, 0, 0 for every column in the row, and one of that for every row. And this we pass along. So we start in the left column, and this we can use to see if if there is another place which is larger.
Not recursive.
Well,
I would say just pick from every point a recursive.
yeah.
But you have to somehow, each path you have to somehow
You
track, right?
Yeah,
you have to always
but you have to path some until now.
1, 3, 4.
No, you have to path some until now, and your function calls define how you went.
Oh yeah, that's
Because
true that you don't
it's
need to
recursive.
remember which one was it. You just remember the number, the sum.
Stack will anyway not go over, say, 180 or so. But you have to remember whether you came from one down, so that you're not allowed to go one back up for the next one.
Well, I know that this is my sum, right?
You have a path sums for
I know
every point.
Yes, I have the.
Cannot.
I assume that. Well, let me put it this way: that this is the shortest. Let's make as a convention, or I guess shortest. So this is shared between everybody, and
You still don't have.
somebody writes into here how long his own path is to that point.
Yeah, that was the current path, the path sum. I mean.
But if another path is shorter coming to this point, then it can overwrite. But if the other one is longer, it stops.
Yeah, that's a good optimization.
But I don't think it's going to be recursive.
Then you have to define the problem. Oh, of course. Ooh. You mean in the third row you have one part, another part.
You should think how they will go, like how to define the
it
options, basically.
It is already something like that you arrive in this cell and have found that there is no path. That there is no path going as shortest way to the end.
Of course, there's always a shortest. What?
No. See, I'm still thinking in the recursive way. You have, if your path sum is bigger, you quit anyway.
The thing is built in the current shortest is like looping through all the paths, and then we only update it if we reach the top right. This is the only way where we can update the current shortest. We cannot decide which way we go.
Yeah, still, because if you arrive with this
Yes.
path, you are on at this point,
Yes.
you have a path sum at this point.
Yes.
If you arrive over
have-
this row, also
No,
at this point, you
I
can
only
quit
can
because
update-
you're already bigger.
The test of the path is superior or to the current shortest is only updated is if I'm at the top right and I have less current shortest less than the what we already found. The
Yeah.
thing that we
Yeah.
needed the current shortest is to not
You have to
continue.
Yeah, you have to
not-
register it on all cells.
Yeah,
Current shortest. So the current shortest to a cell, you have to register that for every cell, because you can encounter that cell in another position, and then if you're then already with your path sum bigger than the current shortest until that cell,
Yeah.
you
So we
can-
don't. There is no possible like path with that current path. So we just quit and
Yeah.
try another thing.
But that is only when you go up or down,
Yeah.
of course.
And
The
if
horizontal-
we, yeah, and if we reach the top right, we can. And of course,
Yeah.
we already reached. So we are sure that we are in. We have a new current shortest. So we updated. And
Yeah,
we-
that was my
we check
line
again.
that I meant after the return in path sum bigger than current shortest. That the next one is, of course, path sum is not is equal, or that should be bigger or
No,
equal.
if path sum is superior to current.
I'm trying to get away from this recursive.
Yeah, you don't want it.
I don't. I really
Yeah,
don't.
It's just not doing it.
Yeah, also my solution is not recursive, so just go on.
Yeah.
Go on,
Go
like
to
instead of brute forcing, it's just optimization using this current shortest, so we don't execute other paths.
I mean, John, if you're really sure that you know a solution, because I can't.
Yeah, I was sure about the recursive.
Then okay, then by all means we can have it that you can write it, because I don't think I'm not convinced that it's a solution. So
I think they should.
I would let you go for a bit and maybe run against the wall or something.
No, I'm not hitting any walls.
I think they are both possible. From my perspective, they should be for sure. I don't know surely, but as I would think, there could be both sides.
Yeah, but
Possible.
I'm still also in favor of that optimization you mean by registering all path sums. For each cell, you have to register the shortest path sum to the from actually until there, and the shortest path sum after that.
Should
probably.
be theoretically faster.
So because the moment that you get
Mhm.
at the cell for a second time, and you had a shorter path,
You don't know
the shortest path from that cell also.
Yeah. Exactly.
So you pick that already right away,
You drop it faster than
Yeah.
you.
and you can do that with every cell, of course. And
Yeah.
that's the same recursiveness, but that makes it difficult to. The mains you have to.
Yeah, really don't have like.
You have to, for each row column, you have to register your current shortest until here and your current shortest after here.
But after here, you don't know it, or
Yeah, one time first time you have to go through, of course.
you have to go through,
And you have to find
each cell you update always, or
Yeah, but while finding that, you get cells further to the right of the columns.
Each cell
And
you update, and then you stop by that if you come there with the
Of course,
highest sum.
in each 79th column, the shortest sum is of course this one, only that one, and then you're at the end. But for this cell, you have encountered that, of course, in this part, and you found for this cell the shortest one is that plus that plus that, of that plus that plus I don't know, but at least.
No, I think you should go up till the end the same way, or like from the second column. You
Oh yeah,
should
for
go-
this one you have the
go-
shortest part is of course that one plus that.
Yeah, but this you don't know on the
Yeah,
beginning.
no, but you have tried this one.
Mm-hmm.
You have registered a current shortest, and then you go one up, and you find that one, and you say, oh, that's even smaller. Okay, then try that one. Oh, that's bigger. Then stop. Then go down. That one is, oh, this is still shorter. Okay, then you have from this cell, you have the current shortest from here already. But you came here over this route, and that was the very first.
And basically then
Now later you arrive over the 201.69 and then there, and you're
Recursively, you would change the path.
yeah, but
and in the end
Yeah,
you see the lowest from the sums.
the moment that you arrive a second time on the 121 on the 497 arrive a second time on this cell, you know already what the shortest from here is.
Yeah. But, but also the advantage, I think, that if you create it, then if you have it on the end, you can see here the lowest number, and you can see here the lowest number, you can see here the lowest number, and see here the lowest number, and you can build up the way, basically.
Yeah, but you cannot select your lowest number because you're on this cell. Of course, there is only one way to the right column. In this cell, you know this one is not the shortest. This one is shorter, but you don't know that yet. So you have to, after testing this one, you have.
But I was already one step. I think I was already by the time you populate everything, basically. Then you can see here the lowest number here, and you see the lowest path where it comes, and you can see the lowest number here, and like this you can reproduce backwards the lowest part.
But by going first time through.
Yeah.
You already have filled in here on the 103 cell. You have filled in an 18. So that one, the next time you arrive at that cell, you already know if you go over this way.
Yes,
you find on this one, you find that 103.18 was the shortest one. So the moment that you go this way and go one up, you find, oh, we have a shortest one from this one, and that is that one. So
yes, I think this is this is.
So it's actually a logarithmic n problem, because you only have the steps. You do all columns to the right only once, because if you're in a cell in this column, you find your shortest way to the end automatically by that recursive. Ooh, this is a long way.
Again, I can't get the backslash.
Backslash alt 92.
Alt 92? This is, do I have to put a 0 or something? Or are you making jokes?
Alt gray 92 with the function key, probably.
Maybe I get it here now.
With the left alt and the function key for the 92 is then the J and the I and the 92.
Maybe I can get it with this magical.
The 9 and the K.
Ja, muss ich zu helfen wissen. Oh, fuck.
OSK. It's Windows.
Okay, whatever.
Windows. The program is start menu OSK.
It doesn't matter.
What is the order? Maybe you do short and order backslash.
I wanted to have the shortest path sums. So, I am pretty sure that this is going to whenever I do while true, it probably is going to break. Okay.
Yeah, but we have already
Okay.
found the principle of the solution. We do not have to do the solution anymore in programming. We have.
You have the analytical solution?
Yeah.
Okay.
The analytical is it's logarithmic n. So
Well,
it's
this
n times logarithm of 80.
I think this is logarithmic too. You only have to. You don't have to go so much. So where are we? I forgot one. I missed one. Here we are. Convert everything with a comma into this thing. No, this is okay. No, this is not okay. This has to be like that. Right, because these are strings, these are integers.
Stir.
Map, stir. Okay, what did I do here? 10 is a little bit not quite what I was looking for. Okay, not quite what I was looking for either. So
You have the test grid somewhere.
this is the test grid, yes. I can print out the test grid also, but I mean, this is up here.
And now you're updating this.
I'm
okay.
trying to update the shortest path sums, yes. Here.
If row is
So let's see.
What is current sum?
Yeah. This is incorrect.
shortest path sums is
Okay, we can start at 0.
First column it will be clear, right? It's like it would be the second column or interesting.
what is that? 0 for call in row.
Where?
That 0 for the line very now. 0 for call in row.
Well, this creates basically this. I mean, here 0, 0, 0, 0. Everything with 0.
No, but I mean, what is 0 for call in row?
Oh, this is a list comprehension. You go through every row. You go through every column in the row, and you put a 0 there.
Call. So call is a number.
I know it's
a number from 1 to row or so.
Yes, I think we can have it more simple even actually.
With 4 loops.
No, it's just so we take the number of things and we do this also times grid then. So I can just print this also. Maybe it's simpler, maybe it isn't, I don't know.
So
if you,
cell, you determine
let me
the
just say
shortest path.
row temple.
So for each cell, you first define a shortest path sums, and then you go through all rows.
Gridland. Did I not put gridland?
You initialize your You initialize your shortest path sums your curve sum every time. Yeah.
But it's not recursive.
Yeah, but you initialize it every time.
Where every time only once.
Yeah, well, path fronts, what's that then?
Only once.
Row 0 for row in the range.
So the idea is we have this grid of zeros where we are going to track the current shortest path. Or we're going to track, so there are two things. There is the front of all of the paths. These are the coordinates. So row and column of the front of each particular path. And in the shortest path, tracking the total sum of the path that leads to that point. So in the first iteration, it will be 131, 201, and so forth.
Yeah,
And
that is the trivial one.
yes, and the second time, it will try and propagate all of them, but only those where it is actually the current sum is actually less than the shortest path. Will it actually be used as a new front, a new possible path, and its sum will be written as the shortest to the grid where we track the sums. So we always have the shortest sum at the point which leads to that point, at the path, at the point which leads to there, and we also have all of the fronts that lead to those points. And yeah, we replace the old with the new always, and we always check, can we go up, can we go down, can we go right? And yeah, if we're not at the grid edge only, of course. But I still need to do something with the zeros, right? Because 0 is always shorter than the current sum, so we have to do something of if
Why not put in big numbers? Because we are testing the small one.
because I do plus here as the first thing.
Huh?
I did that originally, right? I did this 10 to the
Right.
10.
Yes.
So, but I could just go over each thing and put the first shortest paths there.
You just do the
Just
shortest
initial.
path without that plus grid row call.
I see.
Current sum until here, not including, not up and including here.
Yes, yeah, maybe. Okay, current sum is
No, the other one. Just what you deleted.
Yeah, or maybe
Without the grid row call.
the shortest path sums would be multiplied by grid len minus 1. No, because we need the numbers of the first column.
Average.
I'm not sure what the,
What are you now doing? Current. I would say make two loops. Do first fill your shortest path sums array totally.
that is here with 10,000, and then another one which just sets the initial things, maybe.
Why 10,000? I would, for example, as a suggestion, why not to start to go first row, basically, sum it up, basically, and then always somehow amend the way bit one by one, so that you cover all basically options, and then start from the second.
Brute force.
Yeah, because I don't know if like this you get every maybe yes, maybe I don't understand it so well. If you get really every
I think so.
every possible way.
I think so. you always just you're moving through the thing. So at any one point, I mean, I think the way I'm this
Like
I think we'll see this here. So let's see. Let me just put the initial weights in here. So for row in grid, let's put shortest path sums. Like this is this actually. So this is the row, and we take from the grid. So the call is always 0 in the to start with, and we set that initially to be grid row call. So this is now. I might as well make this into a function. Okay, so this is now wrong, of course. How else could it be? What did I do wrong?
Or I have one theoretic idea, maybe it's. But what about to accumulate the rows first? Like just an idea, you know. Just I got the like to accumulate the rows first always, and then from that to start to look. You know, this way of up and down, if you can reach there basically another way.
Yeah, that is what he is doing. But you're missing the direction. If you're going, you have to go 2 times through. If you arrive to a cell from the top, you have to work in this order. And if you arrive to a cell from the other side, you have to go in the other order, because otherwise you'll never find your shortest path sums is going smaller. Because you don't have the number for the next cell yet.
I don't have the number for the next, but I know always the next cell.
You're in row call path fronts, but you don't have the shortest path sums row plus 1. You don't have that yet.
Well, this is a candidate, right? This is what's being done in the new paths. So I'm always creating the next step or the next steps for each thing. So if I'm here at 201, I'm going up and appending it to the new path.
0, you're never going up or down.
Yeah, yes, from the second.
Well, I'm doing it here anyway as it happens, but it shouldn't matter.
Yeah.
Okay, we can do it here for like here.
Yeah.
If we're here, then I'm going up, right? Row -1 and column is the same. I'm appending that to the new path fronts.
For which cell?
For this we're at 96. So I do row -1, go up, and this is then one of the possible paths that we go forward with, right?
But wait, new path fronts. You while being at cell 96.
Yes.
You're modifying the number of this cell.
No. Well, only if I see that the path
over 96 is smaller.
If this is smaller, yes. If the current path that leads to here, whatever the currently smallest path that leads to here, if that is larger than what I have going up to there, this is
is smaller than shortest path sums from that row, then you modify that into the current sum.
Right, and I add that to the next path.
And what is that new path front append?
This is the next candidates which could possibly lead to the new, which are candidates for the shortest path.
Huh?
And basically, it's like moving a wave, right? You go, you have each candidate path. It's like everybody, you have 8 people running around, or actually infinite people running around, but in 8 groups. And then these...
yeah, but that new path front, what is that?
This is the next step. Everybody in these 8 groups, if we start out with 8 groups, everybody in these 8 groups, they see where could I go? I could go here, I could go here, I could go here.
Yeah, but you already did that cell. So you don't have to do that again.
I will only do it if it is actually the shortest path. Otherwise it just goes on, and then the current path fronts is terminated at that point, because nobody adds on to the new candidates, because...
Yeah, but you cannot... Why do you append? You append it 3 times, because if you arrive at the 96 from this cell, you do append, and you arrive from this cell, you do append, and you arrive from this cell up, you do append.
Only the... yes. I think you may be right.
You do 3 times append if you arrive at a very low number cell or so.
Maybe it works anyway.
I would not append. I would just go again through all the rows in that column.
Well,
You don't have to. You have filled in that shortest path on this cell already.
yeah.
You have corrected the shortest path to that cell.
Well, I've corrected
then you're ready.
sum.
You don't have to update, because next you do the next column, and you'll anyway start with take the one to the left.
I'm not sure.
You don't do that.
Let me try and just
For every...
I see what's wrong. Okay, this doesn't work.
I have maybe a bit different idea. Let's say how to, like, what if, like, alternative review probably also works. Maybe not. Maybe if you first cumulate the rows, basically all of them. Basically, you start this plus this plus this plus this. This will be like first step, and then you always test by each of it, like only way up and only way down. And if you get here, like, then you overwrite. If you get to this with the lower sum, then you overwrite. And if not, you stay. And you do this until basically you don't overwrite anything. Because like this, I mean, how you would find this way? You accumulate the sums and you almost have it, basically, and only which gives you the better way is to basically switch instead of this, switch here.
Yeah,
once.
but you only do one level switch. You're missing out the...
But you can do this
it can be
once more.
Yeah, but it can be...
And until you switch
it can give no advantage to switch here, but later on it can be advantage to switch here.
Yeah, just do only the advantage to switch 2 times, yeah?
Yeah, if you... Oh no, of course.
Well, it should be advantage already the one switch only, right?
It is fair. It is to simplify. Whoa. You're going through you have row 0, column 0, you have only numbers. On column 1, you fill in the sum of everything left. That's the shortest path from this cell to the left.
To the left, yeah.
Yeah.
Exactly.
You fill it all, and then you check if there is the cell below is more than your own contents less. So it's actually less if your cell below is less than this one. Then you'll get more advantage to this one via the cell below.
Yes.
And the cell up, of course, if you check. So you say this one comes in from below instead of from the left. And you get your number.
So it can be that, I think it can be that this is not the advantage of go from this but to this, but this one is advantage to go this from this. It has to be also this one advantage. So
yeah,
if you go through this,
but it's easy. Every cell has originally the flag check your parts from the left. So you fill in your parts from the left is this value.
+1 plus
this value. But and then you go one time through with if the cell below you is less than this value, then I'll say this one can better come from this side.
Yeah, this.
And you do that from this the same. If the cell is above, has a lower value than my own left side, then you say I better come here from above and not from this side. So from every cell you only have to register whether you come from the left or from above or from bottom, and you have to register your path, your shortest path until.
Yes, that's I agree fully. I think we speak about the same. I was only thinking if possible to basically build it like a bit more, let's say faster, that you first accumulate the sum, like the row, because most probable is that basically it will go horizontally, because always if you go vertically you just add additional figures.
Yeah, on average, yeah.
On average, and then always try by every column, like compare this on one up and on one down.
Yeah.
And then you see if somewhere some of it, like you get to the lower sum than you are here.
Yeah.
And if not, if you try always all of them, then you are done basically.
But you actually have all cells, and you have to check for all cells only 3 comparisons. So you have 80 times 80.
Yeah, but like this,
and the first times you have to, so you have 97 times 80 and 3 comparisons. Check whether the cell, no, 2 comparisons, whether the cell above is shorter than coming from the left, and check whether the cell below is shorter than coming from the left.
Yes,
and
but
of course
the only
you have to go 2 times through, because if the cell below is shorter than coming from the left, then you'll come over this way. But if this cell, then you test this cell and it says this one is even shorter than coming from the left, then you'll add up this cell too. That doesn't matter. And in this cell you already have registered that. Yeah, but you have to adapt the number here too, because now you're going to test this cell and you have to take the number coming via this route. because that's the smallest one. So you have to go. Actually, you have to go 2 times through.
Yes, absolutely, absolutely
Or
fine.
go back up again.
Only what I was suggesting as possible improvement, like that you would not do it one cell by another, but like that you would do this on
the total, to the
on
right.
total.
Yeah, but I would say you have to fill in. You have to search the shortest route to each of these cells.
Yeah, but I think maybe you will
And
find
then
it
you
also
can
like this.
do the shortest route to each of these. And it can never be that if it is longer until here, oh yeah, then it still can be longer. Then it still can be shorter to reach this cell over here than over there. So you have to anyway test all cells.
I think maybe I was speaking like I was simply thinking that it's not possible that you go. This is faster through the 2 cells, but this is not faster to go here. So that's why I would test always
Yeah,
a whole basically
can
whole
be-
row,
No,
whole
can
row
be- can be-
against the.
no, this is-
you know what I mean.
This is 20, and this one is this is 30, and this is and this happens to be 5, 5, 5, 5. Then this one is still shorter.
Maybe I would like maybe I can try what I mean. I would like if I have it here, I would first cumulate those like.
Yeah, but it doesn't help because the 20,
No, like,
because the
the-
5, 5 does not see that this one is the shortest one. It can be that this one.
I think it does, because like if you would cumulate this and you always compare this cumulative figure to this, then you can immediately rewrite it, and you can rewrite both of them, those, and you like to do it like on a little bit faster way. I was thinking.
Yeah, I get what you mean, but if this one is now 25, it is still the shortest way, because this one is, and this one was also 25. So this one gets over 45, and this one gets over 5, 5, 5, 25, and but you would not.
You can do it more times. You can basically do it like you can up and down until anything move, and if you don't move anything, then you are done.
Yeah.
It's a theoretic still idea, but
Yeah, but you move, and you're not sure that you can need. It can be possible that you need to hop over higher values to get
I
to
don't
get to
think
a
that
lower.
you can over two rows. That if you don't it must work also for one row always.
No, I think they have filled in that matrix with some trick that it is necessary to somewhere skip over at least 2 rows and skip over very high numbers to find
yes,
the
but
short
then
one.
also with this algorithm you wouldn't get there, because it must work also through always to the next cell. Otherwise you will stop there.
Yeah.
I think it would.
No. You see,
Because,
where did you end up?
well, it's not working completely, but I think at least with this output, maybe you can get the picture. So this is always where we're currently the path. These are the coordinates of the paths that we're currently looking at. So we're looking at the path that led to this point and to this point and so forth.
Yeah.
These are the resulting paths, right? These are the paths that we go forward starting from one of these. And these are the shortest distances that it has tracked for whatever the path here was chosen. So if it chose this path, then it wrote whatever the sum for going to this path was into this cell. So 0, 1, so this cell. It wrote that number into here. And then it goes on with starting with this. Does the same thing going forward. Right? It propagates forward the smallest paths it can find and rewrites the paths so that next time it will continue from there. Always continuing from the shortest path. and it goes through, and it goes through, and eventually you see there are no more paths, so the paths start to be consumed, and it ends up somewhere. And it doesn't work quite yet, but I think the idea is plausible.
Your second row is your test grid is not filled in.
No, it isn't.
How do you? This is just double. You added 131 and 131 is
Yeah,
262. That's you missed,
Yeah, I'm
you
saying
missed the
it's not working. Have some mix-ups going on still. Yeah, I'm still trying to figure it out.
Yeah, but it looks that it found on the last column basically.
Yeah, but I have one
first row
addition.
the lowest number, so it
Can
seems
go back
to be.
to this code.
Yeah.
The moment that you adapt a row that you already have been,
Yeah.
you have to check for that row whether the row above still also needs to. So you still have to do. Get it?
No.
The moment that you are in a point here,
Yeah.
that the shortest path to this cell is over this one.
Okay.
You have to go back to this row too, because that one can also be made shorter then.
But
So
then I would have already
actually-
had it from a different angle.
No, because you have only been here over here and there, and not yet over there. Because once you get only if you get on this cell, you adapt this shortest path,
Well, okay, yes.
and then you.
But
have
this,
to
but this
do-
will still happen in the next step, right? If it is the shortest path.
No, because next step is you column further. And you,
Why-
go, you
why-
don't get
I'm not,
it anymore. This
I'm
one
not
has not
always going to the right. I'm not always going to the
been-
right.
You only do one times all rows.
No. Path. The path can go up, down, left, right. I can, right? If this
Path
is
front. Oh yeah, but you're
right, I can go up,
everywhere.
up.
Yeah, but you're every cell you're adding 3 more path fronts.
Right, exactly. From this path, I can go to 0, 1. I can go to 2, 1, or
Yeah,
I can go
that's-
to 1, 2.
Yeah, I get it. But I would do it the other way around. That is the moment that you are at a cell,
Yeah.
you check for the cell itself whether coming from the left or coming from above or coming from down is better. And if the moment that you find out that coming from above is better, I don't get it anymore. No, the moment that don't get it.
I think it's easier if you, I don't know, if you picture it.
Yeah,
like,
I get what you want, but there is some way that you're missing out in direction, in looping through.
I mean, you can just picture just the perspective of one single cell, right? You're at this particular cell with coordinate row, column, and assume we can go up, right, left, up, right, down, and we have a sum here. We have some kind of sum that has led up until this path. Different people, different paths can have different sums going up to this point, right? And they all write into a separate grid, which is tracked in parallel. Maybe I'll just put it in a different color, where the lowest possible sum is tracked. Right, this is the lowest possible sum. Okay, this is called this sum current. And this is the sum lowest. They don't look. Okay, sum current, sum lowest. So, and let me just say, just to clarify, to each of these there is a corresponding other cell to track the lowest possible sum. So I look now. I know what the cost, let's call it, of stepping onto this plate is, or in the cell. So I add S to SC, and I look at the SL in here, and I see, okay, if my SC plus C is smaller than whoever got here before me, then I know that I can step in his place. So I know that this is a viable path going forward. Somebody else got there maybe before me, but I have a lower weight path. Behind me, there was less of a weight. So I rewrite, put my SC plus C in there, and I say, and this is the other part of the thing, this is the paths, right? This is a list of coordinates. So I write my RC. Well, actually, no. I write my R prime C prime. Right. This is the wherever I'm going to. I write that onto here, and the next loop around, all of these new prime paths will be used. Right?
Mm-hmm.
And it may end up being that multiple people go to this. Yeah. This is, I think, what the bug is still, where it's still buggy at the moment. Because multiple paths can come here. The lowest one will be written into here, which I guess is fine. No, it's not fine.
No, you're investigating that before the lowest one is written in. Because you do the next row and then there is a lower one and then investigate it again, but you're extending this.
Yeah, I think I need to make sure that only one of all of the paths here ends up going
that
here.
is it. That is it.
I think this is the problem.
But I would do it differently. I would register only if whether the shortest path is coming from not the whole path, but just for each cell.
Yeah.
The shortest path is coming from up or left or down.
But I don't know what the cells are that I'm looking at for the moment.
And the current shortest path value.
But the cells change, right? I mean, it's not as if I'm just looking at one column. I'm looking at an arbitrarily shaped...
that is your thing, but yeah, true. But I would say go only one time through, and if you go through and you go up, you have to do that cell once up, so you have to do that in a sort of recursive function. To check if cell is better from down.
Yeah.
Oh, and the other three functions. Check if cell, if cell has a value from the left, and just check cell from down better, and check cell from up better. Then you go through the whole loop, and if you have somewhere you find that the cell from down is better, you have to do that again for the cell up.
It sounds so complicated. Maybe it's just me.
It's much less lines.
Much less lines. Did you say that solution is less lines than this?
Yeah.
I don't know.
Now you have a path front, but if just go in there was this solution. So for each cell, you just check if the row is bigger than 0, then you have to check if up is shorter than left, and if so, then replace your arrival with the one from up, and then you do also check if from down is better.
I think I'm too tied up with this thing to follow up along with what you're saying. I mean,
I'll do something later at home. But it is getting.
So I think what I will do is I will do a dictionary and I will map the, so we'll track what the new paths, so this will map from coordinate to the weight of that path. Right, so this is the next thing, and if the, I mean, it could be that multiple paths
just
lead to here.
register new path front. What is that? Just register in each cell if it is still eligible for the shortest path. Just
Why each cell? It's not the cell, it's the coordinate.
Yeah, and each coordinate.
But that's what this is, isn't it? I mean, if it isn't eligible, it will not be added here. These are the currently eligible ones in, yeah, together with their weight, which is what you need to determine if they're eligible. Or I guess I call it path sum.
Yeah, but still, you do new path front append.
Well, yeah, that has to change now.
3 times, and that is.
Well, why I have to. I mean, from each coordinate, it's possible that any of those that either of these can go be the way that the shortest path could be. So I have to check every one of them.
Yeah, you're checking from each cell the possible that the other cells that it can add to. And I would say take in each cell the way it can best come from. In that way, you go through one column, and if you find that it can better come from the bottom, you need to do your previous cell also.
But
just adjust your previous cell.
Okay,
you need
so
to
you're saying so you're saying I'm at 803.
Yeah.
And you say I should look at the 9.6 because that is the shortest, that is the lowest weight of the 3 options I have.
You just go through from 673, you say 96, that has its shortest way coming from the left. Then you are on 803, it has its shortest way from the left is 630, but its shortest way from up is, you already have filled in that number. That was 297. So say my shortest way to here is 297 and it is from up. Now you get to the next cell, 699. Assume that 699 is actually you can only check the shortest way from up because you have not done 699 yet. So you, oh yeah. So if you are getting at 699 and you say my shortest way to arrive here is from the left, then you need to check whether it is better to go up. Whoa, it's a different programming routine. So for each cell you have to check whether it is better to come.
But you don't
from the one before.
And
overwrite
it only in case it's lower, or?
Yeah, and if it is better to
like this one.
come from one. So for each cell you have a base number coming from the left, but you're passing one time through. The moment that you're in this cell, you need to check whether it is better to come to this cell from above. And if it is not, you have to check whether it is for the previous cell better to come from below. And if that is true, then you have to go one cell back further up. But it's just a function to
This is so intuitively wrong to me that I have to look beyond the currently things around me. This is, if I have to look one step further, this sounds completely wrong to me. I should only care for my neighbors and maybe some global state. but always picking out the global state using the coordinates of my neighbors. That seems to me that the solution has to look like that, because the moment I start, why do I stop looking only at the next coordinate? You say I look past.
Yeah, you only have a choice of coming from above, or from the left, or coming from down.
Yes.
You can also go through 2 times through. You go 1 time through with only checking if coming from above is better, and go from bottom up to check whether coming from downstairs, from down cell is better. So in each row you have only 2 pass-throughs, 1 down, 1 go up.
Well, I think this should be based on some minimums. You know, in every cell should be basically the minimum cumulative sum altogether.
You first you fill in you're coming from the left, and then you go 1 time through if coming from above is better for each cell.
Then it depends. If this sum is lower, then it will be there. If this sum is lower,
so each cell you check if coming from above is better than coming from the left. If coming from above is better, then you fill in I'm coming from above and fill in the new pass sum.
Exactly, and this,
and then you go down, and then you go 1 time up because you also still have to check whether coming from below is better.
Yes, but I think it does, right? He goes from upper right down.
He's doing some say it is going in some graph, and you never know whether you have doubles in your graph, and that is.
But if you go for minimum sums.
No, you cannot do the minimum. You have to do the minimum on each edge of this graph.
Exactly, on each edge of it.
But it is going anyway, passing through all, and you have them. Maybe you have them double. If you can leave them out as doubles, but you're anyway doing 3 comparisons on each point, and I find this graph so. You only do. It is just as efficient because you have. But you have to count that you don't fill in your points double in your graph calculations.
Yes, definitely.
But you go through and you have for each point you calculate the shortest route to get there.
The minimum cumulative sum, basically.
I don't like that graph thing. I like to do progressive. There's 2 calculations needed for every point that is coming from above or coming from below better, and that's all. So you have to go down and up.
Okay, so if I understand correctly, you want to do 4 column in range grid len. So if we go from left to right, then we go up for row in range grid len. We go from top to bottom. We do that once, and then we go from. It doesn't actually matter. We can do the comparisons here. We can look. Okay, so we're looking at every cell. Now we're checking. We're looking at every cell. We're looking at above, below.
No. And 1 time for
unfortunately, I have
0 to. You have to leave?
Very sorry, I have to go by train. Like I live behind.
I'm still curious whether this works. You go 1 time from row 0 to 79 for checking if.
You mean all the way to the right?
Thanks a lot.
Thank you.
Thanks a lot. No, it was really fun. Really fun.
Yeah.
Thanks.
So,
I'm sorry that
every 2 weeks, right? You can
I'm sorry that I have to leave.
That's no problem. It's no problem.
You know, I would need to.
Next time you'll find the solution.
Bye.
Why do you go all the way to the right?
No. All the way from columns. Columns. You have for each column you do 2 passes. Row from top to bottom and bottom to top.
Why 2 passes? I mean, first, you want to look at above.
From top to bottom, you can check whether coming from above is better.
But can't I?
For each column in range, yeah, you start for each row. Yeah, you have for each row in range. If column is 0, you just fill in your shortest path is your own number. You have to pick that up.
Wrong. This is the grid.
Yeah.
Let's just do. We can do it. We can start at 1, I guess.
Yeah, of course. Yeah, but you still have to fill in column 0.
Yeah.
In the sums.
Yeah. So this is then row.
Yeah. Yeah, that is range column row and range is 1 to grid length.
We're going row, right? We're going row.
No, but the first thing, the first
yes,
the first loop. The first one 3 lines up. Yeah, there.
What about it?
Row in range. Isn't that 0? That grid length? Was it?
Didn't you want to get the left? Didn't you want to?
No, just fill in sums in row 0 0. Sums 0 0 is not filled yet.
It is.
Where?
Pardon me.
Yeah, there maybe.
No. I want this function here.
Just.
Sorry.
What is that?
This is a grid with zeros.
Yeah, but in this loop, you fill in sums is equal to grid. In this loop, for the left column, you fill in sums. In row 0, you column 0, you fill in rows. You fill in sums is equal to grid. In column 0.
So. Oh, yeah, that's also there?
Yeah, that is what I meant.
That's what you. God. Sorry, yeah. Hab's nicht gesehen.
And then.
Okay.
Print grid, yeah, that can go.
Okay.
Now you do column in 1 to grid length, yeah. For row in.
Okay,
again.
so here we go.
Yeah, if row is 0, you don't have to check. So sums is only.
Okay, so the first one we only have to check.
No, for row 0 you have to do something. If row is 0, you have to do. Oh no! First do sums row in the whole range. Sums is myself plus the left.
Right, that's the default. Right, exactly. Okay, so for the current column we go row.
Oh no! No, wait.
So this is column -1. So we start off with adding the grid. I suppose it's the grid of the current plus row.
No, you don't have to fill in your own.
Actually, this is the same thing as this, isn't it? It's just.
No, not row and sums. Row column is sums plus myself. Now here you start already with if.
That doesn't look right.
Yeah, clear. Wait, there is no if in the whole thing. Wait,
yeah, not yet. Yes.
Yeah. Next one. Sums is if row is greater than 0, row same in the for loop. In the for loop, if row is greater than 0, and if sums, I don't know if sums row column.
What are you trying to do? What did you want to go?
Now, if 1 less row minus 1, sums row minus 1 call is smaller than row call minus 1.
Yes. Well.
Yeah, is smaller than row.
Whoa. So above us, if above us is less than this.
Left. Yeah.
Why left? Current.
No, left.
Okay, fair enough. It doesn't. So this means I do.
Yeah.
We don't do any of this yet, do we?
It's actually not necessary, that line. That you can come one later. Oh no, only for row 0. If row is 0, you have to fill it in, of course.
If row is 0.
Yeah, it's valid in the first loop.
But that's only for the first line, right?
Yeah, row is 0. No, second line. This is the second column already. But the first row, you have to fill. You have to take the number because there is no if possible. You cannot check if the top is better.
Yeah.
Didn't we do that in the for row in range, just the previous loop?
No, but you have to fill in the number. Just see if row is bigger than 0 and sums row minus 1 is less than. Oh yeah, that's all. And there is an else, of course. Leave out this one. This one is the else. You fill that in and this line is the else. So it's the else from that if. So, and if the row is bigger than 0 and sums row minus 1 is less than sums col minus 1, and left side of right side of that, see that row, that if statement.
Yeah.
At the right side, the col should be col minus 1.
Right. Right. If above us is cheaper than to the left of us.
From the left, yeah.
From the left.
Minus 1.
Yeah.
Then you fill in yourself from above. So there's a copy from that one, but then.
Yeah.
But then with that one, yeah.
But this isn't necessarily the else, is it?
Yeah, the else is from the left. That is all right.
Well, it's.
That's for row 0 and for all where from the left is better.
Shouldn't we want to do this below one too?
Huh?
Shouldn't we do the case where we're below us also?
No, that's later. That's a second for loop from back to grid length to 0.
Okay, I'm a bit worried because we're already doing the sum on here, and
for yourself.
Yeah, maybe it works. I don't know. Let's see.
Yeah, you have to count yourself in it already.
Yeah.
That's your sums. Your own sums is depending from whether it is coming from above or from the left.
Okay.
And in each of these cases you count the one from above or from the left.
So where is this going wrong?
Huh? No, wait.
Oh, sums.
Oh, yeah, sums. And now you have a second for loop.
Yeah.
That is for the other way around. Yeah, take it whole. But
It doesn't have to be the other way around, does it? It's just
Yeah,
that
it's
we're
just-
comparing to +1. To
No,
plus
it has to
one,
go.
yeah.
It has to start at the bottom
Why? Why?
because otherwise it is not adapted.
Okay.
You take the value from the bottom in your own, so you have to have been there before. Otherwise, it can be that you have to go 3 times up, 4 times up. So you have to start at the bottom.
Huh. Maybe.
This is gridline.
This.
You end on 0. Gridline +1, gridline -1. Then.
Let me just show.
Yeah. You start at this one too many.
Start is inclusive.
No, yeah, you have to do gridline -1. Then. 7 to 0. 7 step -1 to 0.
7. Okay, I see. I see. Yes, because we don't want to go look down. Okay, fair enough. So gridline -1.
And step -1 and
Yeah, it's probably easier to do row is gleich
Yeah.
grid then minus row, right? Then we start at 0.
no, then you have to count row. Just do another.
Yeah, but we do the same
but
thing as here.
Name the variable row back also.
Yeah, okay. Row.
Nein, das fängt doch an ganz am 0.
No, because we're going reverse. Because we're subtracting again. Gridline is 8.
No, you cannot
minus...
adapt the row. You cannot adapt the same variable. Row B or the.
Well, I mean, I can rename it.
Yeah, that's so.
I mean, it's clear, yes.
But it has to start at.
Gridline is 8. We start at 1. 8 minus 1 is 7. Row, the first row we look at is 7. We go up to gridline is 8.
Okay. Row
with non-inclusive, so we end at. This may or may not be. Wait a minute. The last one is 7. So 8 minus 7.
No, you have to start at same. Start at 0. Start at 0. Underscore row is 0.
Yeah.
Yeah. And now underscore row is bigger than 0. No, that is right, but 2 lines further. The if is underscore row is bigger than 0. The first time.
Okay.
Again, yeah. And sums, and dat is dan weer gleich. Row minus, that's row +1.
Genau.
Row +1 is.
Das war's, oder?
No, you already have a value. You already might have a value coming from above. And the value coming from above is
right. So we have to have another if clause here.
No. It's just
we can't just set
row
this.
plus. No. It's here. It's just row sums row plus this one. So instead is smaller than.
What plus? It's also the issue is here that we already added the grid thing here onto the sums.
Yeah, so you have to just count that also with the sums plus my own. So your own grid row call. Sums row +1 plus grid row call is less than sums row call -1. Yeah. And now less than sums until now. Dieser.
I don't know where you're going.
I'll spell it. Sums row plus 1 call.
No, before you spell it, you can.
No, I just read. Sums row plus 1, I mean, plus sums plus grid row call.
Where am I adding? What am I adding? Plus
There, plus grid row call is smaller than sums row call without the -1. So that is my current value. If my possibility to come from below plus myself is less than the other sums plus myself until now, and the rest is the same. Sums call minus oh, the other one is not right. The last one, the else is not right. That's here the else is just sums row call is sums. No, that has to stay. That has to do nothing because it has already been filled. So there is no else. There is a list index out of range.
Just here. I have to pull it up maybe.
If no, it's not. No. Down sum is it actually? But yeah.
Oh, okay.
Sum. If cursum, you don't have cursum. If down sum, yeah, again, down sum is less than sums until now, then sums until now is down sum. Yeah, that's it. That. Row plus 1. What is row? And yeah. Yeah. Wow, 1, 4, 1. 1.
So row wäre 5.
Nicht gut. Es sind nur 4. Ich max 4.
Richtig, ja. Nee, sind 5 insgesamt, aber...
Nee, row ist 1 zu 4.
Ja. Index 0 bis 4
Ja,
inklusive. Genau.
Underscore row is 0 is 0 until 4.
So, aber das geht jetzt... Das ist
Underscore row is 0 to 4.
Right.
Then row is gridlen -1 minus underscore row.
Okay.
Nine 4. That's the answer.
Ja. Könnte hinkommen. So, und die Antwort ist aber dann
The kleinste, the smallest one from right in the right column.
Für Row die letzte for Row in Sums.
That's big.
Oops. Yeah.
Huh. No.
But I
You saw how quick he did that. You did
How quickly close, you mean?
Your conclusion was,
you mean
okay, this is working. Now, then I'll do the grid. Okay. Also, okay.
Next one.
yeah. But I will say this fuddling with indexes in my mind is less elegant.
Yeah, I get it. The graph is much more elegant.
Yeah.
No, you can do that. This one, the underscore row, you can do in a much better way, of course.
Yeah, what is the way to do this? I mean, we can just do
For
the.
row equals
Let's just do the quick.
gridlen -1 until 0, step -1 or so.
Yeah.
And then
Until
underscore
0.
row
You have
is then-
to do all of the things.
And a row is less than gridlen plus
Yeah.
1. Oh, gridlen -1.
Well, it always is, isn't it? We start off to begin
Oh, you
with.
start at gridlen, yeah, of course. And there is no else, so it is alright.
Or not. Let's see.
There is an underscore row, maybe? No?
No.
Now you start at gridlen -2.
Yeah. Took me 1 week. Oh yeah.
And what are they doing?
What are they doing? They're doing.
A lot of undeclared variables or variables x, y, a, o.
What the? What is this?
That's the 1000 square or so.
Maybe. Yeah.
No, it was one digit more. It's 10,000.
Jesus Christ.
Doing and
Okay, but he's going through each.
How many
This is x,
comparisons?
y, this is column, row, column, right?
And then he's doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, 14, 16. A lot of too many comparisons.
Something special about this number.
And a lot of additions.
smallest.
He's starting at this number.
Maybe he's sure it's the list like big infinite.
Yeah.
Just big number.
Yeah.
Unbelievable. This is not the right one. Not the right one. Next one.
This is
I'm looking
invalidly
for-
not
I
acceptable.
want to see the
Is
J.
it high?
I want to see the J one-liner.
Yeah, well, we can only hope. Mathematica is close enough, isn't it?
Transpose.
Jesus Christ.
There is transpose.
Transpose,
And
reverse,
reverse.
rest, fold, list.
But this is just producing the grid, I think.
Yeah, and then rest A plus min.
Oh, there is min path predefined.
Oh yeah. Okay.
Well, min path.
This fold, I think, one of the like dash extra. There is N1 fold is just applied one of the min path algorithm.
All I needed was a few applications of the fold ID with this common functional programming. Strangely, the important bit is the f function.
So we add on the min of some other thing. Okay.
X, A.
What is even x? Is x global? No. What? I don't
X
understand.
underscore.
Like iterable maybe X.
What is x?
Like iterating over whole thing maybe.
I don't know.
Rest fold list. I think this is a help function used in fold.
There is
There's your j.
J. Whoa, that is elegant. And it is clear he's doing only a few comparisons.
Well, how is that clear? I don't see how that's clear.
I don't see any clearness. This.
I don't see any comparison here. F computes the minimal sums for two columns. The overall answer obtains by inserting F between the columns of M, between the rows of the transpose of M, then finding the minimum of the resulting vector.
Okay.
I find how we did it in the end. My up down thing. I find that most elegant.
That's okay. It's okay.
Hey, that's a graph method. You see, with
Where?
parts and so.
This is a graph method.
Yeah, it seems. In computing the minimal sums for two columns, one need to consider the parts that go up or down in the first column, then across the second.
Yeah, same.
He's also doing some graph stuff, or within J in the one liner or two liners.
Forget about cycles on my first attempt. But couldn't be any cycle because they shouldn't go back.
Yeah. It shouldn't go back, and it's always.
Yeah, maybe he's applying something like in general. So
Yeah.
can we read the solution?
I'm not sure.
The bottom one, the Nitten.
Yeah, that one.
Python.
Search.
What the?
Except key error.
Except here.
Oh, import Python.
Whence you came, left by default. Yes, if all else.
Whence is that
There's English word for old English word for some previous
some time ago.
Whence you came. No, not necessarily time. I think it can also
This
be
is a recursive way. Is colon
Yeah.
search again.
left, above, below.
Were he testing below above?
He's also deciding between left, above, and below.
Yeah.
That is the thing. That is you have. That's. But he has the same problem if he runs through, and he checks above before he checks allow below before he has sure that below cannot come from further below, then he is wrong.
I don't know.
You can only check whether coming from below is better if you
It has
filled
to.
that below already in, because it can come from further below.
But it has to be symmetric. That can't be the case.
Yeah, you have to do one time from up and one time from below.
What is the value of I?
I comes as a parameter here. This is basically row column. Is I.
0.
No.
0, 0 as first.
No. This is the row.
Yeah.
I find this one is a better programmer because he has a very elegant line for filling the matrix.
Yeah.
The M is a matrix of int x for x in L dot split on the commas for L in F. That's a nice.
Yeah, it runs in about a third of a second.
Yeah, I think the third of a second is opening the file. And then it runs on 1,000 of a second because.
So you're saying that this is more elegant than my.
Where was your? Oh no, of course that is.
Furchtbar. This is no comparison.
Grid is int cell for cell in line split. No, that's the same. But I did not know how to. I would not know how to do it in Python. I know you know the
Yeah. No.
That's still Python.
No.
No, I was thinking, hey, Visual Basic. Hey, the next one is Visual Basic.
It doesn't show a solution.
I misunderstood the problem. Every place on the column, the smallest sum to the seventh shortest route to the previous column. Then it moves through the matrix from the left. Confusing x and y. Next one. There's nothing.
I'll go by the upvotes. If it doesn't have an upvote, probably not worth.
Yeah. Matrix.
So he initializes what? Max. He initializes max, so this is his grid where he's calculating what? Something? Yeah. He's initializing it to some large value. He's initializing the leftmost, I don't know, maybe this is column, row, I don't know.
Left.
To
it's also,
0.
He's also defining sums, and then for each column
he's taking it from the matrix.
Yeah, and then for each column he goes one time down and one time up. He only has very dangerous comparisons here.
Well, he goes for each column and row. He goes through a whole grid.
Yeah, from left to right, and then...
Yeah, from left to right.
And then from each column he does a row going down.
Yes. Yeah. Right, so...
Oh no, he checks minus 10. He checks if you have to come from 1 or 2 or 3 or 4 up. And I just found it so nice that if you have on this one, you have coming from left or from up already, you only have to decide on this one if you have to come from up or from left, but not anymore from 2 or 3 up, because the cell before you had already decided whether it comes from left or from higher up. Mm-hmm. So while going down
the corner.
Ja.
Ah ja. Machen wir Schluss, oder?
Ja.
Schauen noch kurz, ob's.
Nee. Dynamic is each cell starting from the left moving right. Each column must be iterated over thrice, once for each legal direction.
So we go column by column. We have initialized to.
Yeah, and then he initializes it to coming from left.
So this is the optimal, I guess.
Yeah,
so,
but this is that's coming from left. Just fills it in.
No, he always. This is the filled.
No. This is filled. No, that's the.
Here he has his matrix.
Yeah.
And his matrix, he goes row by row and takes only the first, so the leftmost column, row 0, and he inserts that into a list. So he has a list of one element, and that is the leftmost values. So that's his optimum. And then he appends onto that. What does he append onto it? He appends onto it the current and the previous, the one to the left, right? Here he appends onto the current row the thing from the left.
Yeah.
That's how he starts.
Yeah, and then he checks from top to bottom.
Then he checks from top to bottom, and
better,
then
better
from bottom
the
to
top.
top
Is better, and then from bottom to top.
Reversed. Why didn't I do the reversed? Why didn't I think of reversed? Reversed is much better.
Yeah, but he is doing way too many variables, and opt and m and row.
They really have more than we.
I don't get how he does the opt.
But isn't that just the sums?
Oh yeah, of course.
He's adding on the sum.
Yes,
It's just the sums and the grid. It's the same thing.
Oh yeah.
But this is interesting for me. 4 row in reversed
Of course.
range grid len.
No, 1 to grid len. 0 to grid len. No, range grid len. Oh, of course. Yeah, no, grid len. Oh yeah, -1.
Minus
yeah.
1.
Yeah, that should be it.
And we go.
Yeah, that's,
Yep,
that's
I think this is it, yeah.
Yeah, it's better. 263, 24. Okay.
Nice.
Better.
Yeah. Yeah, and then he checks above. If this is larger, he checks below if it's larger. Yeah.
I find it, this one is beautiful, but I find with the else in the first look nicer.
Why can he save himself the else?
Because he already did the initial.
Yeah.
He
I
does
see.
one assignment too many.
Yeah, okay. Well, he only appends. Does he ever overwrite anything?
Yeah.
Yeah.
The
okay.
optrocal.
Yeah.
The optrocal is overwritten here.
Okay. And this looks pretty much exactly the same. Oops. Yeah, that's same.
We have the sum strocal, but it's only overwritten if coming from down is better.
Yeah.
Is it Lisp? Yeah, I think it's Lisp.
Well,
It
could
is.
be scheme.
Ah, scheme.
But he didn't get the formatting
It
right.
took half an hour and runs in about 1 second. Don't like this.
Ooh, memorize.
Memo eyes. No, don't like that. I don't like
Functional programming.
lambda as a variable.
No, I think